We're now going to have a look at thermodynamic potentials. Thermodynamic potentials. Now, what is a thermodynamic potential exactly? Well, we've actually already met a couple of these thermodynamic potentials. They're just kind of terms that we use a lot in thermodynamics, but we use them in slightly different ways, and some of them are more useful for different processes than others. We've come across U, which is the internal energy, and we've also come across H, which is the enthalpy. Now, you might have heard of enthalpy from chemistry, because it's actually a thing that you use quite a fair bit in chemistry, the enthalpy, because enthalpy, as we found, was useful for when we were doing the heat capacity at constant pressure. And for processes at constant pressure, for which a lot of chemical reactions happen at constant pressure, then enthalpy is a pretty useful thing to measure. Whereas internal energy was useful for things at constant volumes. So we're going to introduce a few more thermodynamic potentials in a little while. But before I introduce them, I just want to cover a little bit of maths, which is going to be quite useful for us coming up very soon. And it's going back to the idea of the exact and inexact differential. And I'm just going to go into a little bit more of the maths about what an exact differential actually means. So let's say I have a function f, and this function is of two different variables. It's a function of x and of variable y. These could be absolutely anything. We'll find that they all will have uses for in a moment when we think about how to apply these to thermodynamic potentials, but for now let's just keep it completely arbitrary. F is a function of two variables, x and y. Now, it's a fact of maths that the full differential of f is equal to the partial differential of f with respect to x, keeping y constant, multiplied by dx, plus the partial differential, I should say, of f with respect to y, keeping x constant, multiplied by dy. And so we've got these two kind of funny little terms in here. Now these are partial differentials. They're not the full differential here. They've only been differentiated with respect to one variable. So let's just have a really simple example. So let's just say that f equals 3xy. Now when I partially differentiate something with respect to x, holding y constant, then I basically just treat y as a constant. So I treat it as if it's like a number, and then so I can just literally take off the x, and so I end up with 3y. So that's the partial derivative with respect to x, keeping y constant. And of course vice versa, if I differentiate with respect to y, keeping x constant, then I end up with 3x. So that is basically the partial differential. You treat the other variable as a constant. Now I'm going to call this partial differential right here, I'm going to give it another letter. I'm going to call it p. I'm going to let p equal the partial differential of f with respect to x, keeping y constant. And I'm also going to give this one another name. I'm going to call it q, and I'm going to define q to be the partial differential of f with respect to y, keeping x constant. So I'm now going to rewrite what df is, and df equals p dx plus q dy. Now p and q could be functions of both x and y. In this specific example here, it turned out that p was only a function of y and q was only a function of x. But more generally, p and q could both be functions of x and y. So now what an exact differential is if I take the derivative, the partial derivative of p with this time respect to y, and evaluate it, then if the differential is exact, then you get that dp by dy, this time keeping x constant, is exactly the same as the derivative of q with respect to x. So let's just think about it. So what was P and Q? P was the partial derivative of f with respect to x, keeping y constant. And now what have I done? I've differentiated this P now with respect to y, keeping x constant. So I've essentially done two differentiations, but with respect to the two different variables. And the same applies for Q. You know, Q was initially the derivative with respect to y, and then I've differentiated Q with respect to x. So this is the condition. It's this condition right here, which is true only for an exact differential. And what we say is that for an exact differential, the cross derivatives are equal, and you can kind of see why I call them the cross derivatives, because you first do x then y, and then the other way is you do y then x, so they kind of like cross over a little bit. So that is the condition for an exact differential. If I was to write it in terms of f, I would write it as d2f by dx dy is equal to d2f dy dx. So basically it's saying that if the differential is exact, it doesn't matter which way around you differentiate it. So you could either differentiate f with respect to x first and then with y, or you could differentiate f with respect to y first, then x, and either way you get exactly the same result. Now if we look at this example here, we find that our p value right here is 3y, and our q value is 3x. So what is dp dy holding x constant? Well, there's no x to worry about here. So we get that dp dy, for this case, dp dy is 3. So we just simply take off the y, and we end up with 3. And you can probably see that dq by dx is also 3. So what have we got? Well, we got dp dy equaling dq by dx, and so therefore this f right here is an exact differential. It satisfies the condition of an exact differential. And all of the thermodynamic potentials, the internal energy, the enthalpy, and the others that we're going to come on to in just a sec, it must hold, because they're state variables, that the differentials are exact. And from these you can kind of get what's called the Maxwell relations, which we'll come on to very shortly. And these are some very useful relationships which you can use to convert between different variables for different things. But yeah, we'll come on to them very, very quickly. So, and now let's move on to the fundamental relation of thermodynamics. And you're probably wondering, what is that? Well, it's actually almost the same as the first law of thermodynamics, except we replace the inexact terms, which are the heat and the work, with more exact terms. But in doing so, we have to make an assumption. So let's go on to this, the fundamental relation. So what is the fundamental relation? Well, what's the first law of thermodynamics? Let's take it in its differential form. So we have that du equals dq plus dw. That is the fundamental relation of thermodynamics. But what did we say dw was? Well, we know that dw is equal to minus p dv. So, well, we can immediately just substitute that in right here. So dw equals dq minus p dv. And what you can see is this dw, this inexact differential, has now become this exact differential. Now, we can do a similar thing with dq. What did we define entropy as in the last video? Well, we defined entropy ds is equal to dq over t, but only for quasi-static processes. So only if the process is quasi-static. And that is the assumption that we have got to make right here. We need to assume that the process is happening quasi-statically for us to do this substitution, because otherwise the substitution won't work, because if it's non-quasi-static, then you don't get that it's equal to, you actually get that it's greater than or equal to, which is the Clausius inequality. It's actually the second law of thermodynamics. But if we assume it's quasi-static, then ds equals dq divided by T. So what are we going to do? Well, let's just substitute that in. So we're going to get that du equals, rather than dq, we're going to write T ds minus P dv. And this right here, this is the fundamental relation of thermodynamics. du equals Tds minus P dv. So you're probably thinking, wait, will this work all the time, or will this only work if it's quasi-static? Well, amazingly enough, it does actually work all the time, because even though this equation and this equation right here only work for quasi-static processes, the two exactly cancel each other out for this relation to still hold. So if T ds is greater than dq, then minus P dv will be less than by exactly the same amount. So this is always true, and it's why it's called the fundamental relation of thermodynamics. Now, until now, I've completely kind of ignored this term right here, n, the number of moles, or equally you could write the number of particles right here. So yeah, I've completely ignored what that is. I've not treated it the same way as I've treated temperature, pressure and volume, but that's because until now we've assumed a closed system, an isolated closed system, and so therefore I've said that n never changes for any sort of process. N will never ever change. However, what if I open the system up? So here's our box of gas, and as well as having a heat bath around it, as well as it being in a sort of a heat bath to allow the temperature to change, I also sort of make a sort of maybe an opening right here. I open like a partition, and therefore particles can come in. Well, the system is now open, and therefore this right here is no longer constant. This n is no longer constant. So what's this going to do? Is this going to undo everything we've done so far? Well, thankfully not. Well, what we can do is we can define a thing called mu, which is the chemical potential. Well, I'm now defining a new term which is called the chemical potential. And the chemical potential is essentially the energy per particle, or the potential energy that a particle has as it moves through its concentration gradient. So say you have maybe sort of some particles here. You've got some particles here in a gas, and you've got some particles at this end. But the key thing is, at this end, the particles are much less dense. There's a far lower concentration of particles at this end. I'll just write that word out. It's all about the concentration. There's a far lower concentration at this end than there is at this end. And so what's going to happen if we sort of just let the system do its thing? Well, the particles are eventually going to spread out until they're kind of all kind of at the same concentration. This is what's going to happen. You know, it's not going to naturally stay like this for very long. It's just going to spread out until they're all sort of roughly uniformly distributed. And so what the particles have essentially done is they've moved down the concentration gradient. And so what we say is they've moved from a region of high chemical potential to low chemical potential. So the chemical potential is essentially a measure of the amount of energy, the amount of potential energy that there is to be had as a result of its concentration. So if you want to know the difference in chemical potential between two regions, so say you've got point 1 and point 2. So let's call this point 1 and call this point 2. Point 1, as you can see, has a much higher concentration than point 2. If you want to know the difference in chemical potentials, well, it's actually related to the natural logarithm of the concentration. So the way we write this is that mu1 minus mu2 is equal to RT times the natural log of the concentration. So I'm going to let C be the concentration. So C is the concentration at point 1, and C1 is the concentration at point 1, C2 is the concentration at point 2. And the concentration, I should probably write this out, is just literally the number of moles per unit volume, or equally the number of molecules per unit volume. It actually depends how you define the chemical potential. Sometimes you use the molar one, sometimes you use the molecular one, but you can easily convert between the two using the Avogadro number. I'm actually going to be using the molecular chemical potential, so I'm going to slightly change this formula. Rather than using the molar gas constant, I'm going to use the Boltzmann constant. So all I've done is I've just divided by Avogadro's number. So the concentration, so the chemical potential is per particle rather than per mole. But of course this ratio won't change. It doesn't matter what concentration you use. The ratio is going to be exactly the same in either case. So that is the chemical potential. And a more thermodynamic definition of the chemical potential is that mu is equal to the derivative of U with respect to the number of particles. So as I said, it's the energy, sort of the energy per particle, keeping the entropy and the volume constant. So that is our definition of chemical potential. It's the energy per particle. It's the potential energy per particle. So going back to the fundamental relation, then I can actually expand on this change in internal energy, because if we allow the system to be open, then not only can we have heat being done to the system or work being done to the system, but we can actually have an increase of chemical potential energy due to varying particle numbers. So we had TdS, like before, minus PdV, also like before, but now we're going to add another term to it, and it's mu dN. It's the chemical potential multiplied by dN, the change in particle number. Technically, particle numbers are discrete, but we're going to kind of pretend that they're continuous. Because they're so small, we might as well just think of them as continuous, so that doesn't really matter. And you could also even add that other variables may change as well. So you could also have like a sum maybe of this other quantity times this change in another quantity right here. You could have anything really. Anything could affect the internal energy of a thermodynamic system. But we're not going to think about other factors. We've already introduced this new one. Let's not get too ahead of ourselves. So yes, that is the fundamental relation of thermodynamics. Now I'm going to go back to enthalpy, H. And what did I define the enthalpy to be? Well, I said that it was simply the sum of the internal energy plus PV. And the reason this enthalpy worked was because it directly gave us the heat capacity at constant pressure pretty nice and easily. And so adding this extra PV term kind of worked. But let's take the differential of enthalpy. Let's take dH. So how are we going to do this? How do we take differentials? Well, we can simply take the differential of U fairly easily like that. But now we're going to take a differential of a product. And so when we do that, we use the product rule yet again. And so taking the differential of this, we get P dV plus V dP. We've done this step a couple of times. It's just the product rule. P could change, V could change, and so therefore you have to add both contributions together. But what did I say was du? What did I say was du earlier? Well, du is TdS minus P dV. So that is du. I'm going to ignore the chemical potential for now. I just wanted to introduce it just so that you guys were aware of it. But I'm going to drop the chemical potential term for this little bit. But we haven't finished yet, so we've got to keep writing. Plus these two terms right here, P dV plus V dP. Now, what's going to happen? Well, dH equals TdS minus PdV plus PdV. Well, that's just 0. So both these change in volume terms just cancel each other out. And so therefore, we get that the change in enthalpy is TdS plus VdP. And so therefore, we've kind of ended up with two different natural variables right here. We've ended up with entropy and pressure rather than entropy and volume, which is the case for the internal energy. And we call these two variables right here, the ones with little d's before them, the natural variables of the thermodynamic potential. So internal energy, let's write it down here. The internal energy kind of had its natural variables as the entropy and the volume, and also the particle number n. But let's just forget about the particle number for a sec. So the internal energy was a function of entropy and volume, but enthalpy, we can see, is a function of entropy, just like internal energy, but it's also now better with pressure. You know, enthalpy works much better with constant pressure, as we found with heat capacity. And so the natural variables of enthalpy are the entropy and the pressure. So I've got this expression for the change in enthalpy, which is dH equals TdS plus V dP. But what did I say was the form of a full differential before? What did I say that it was? It was dF equals dF partial f by partial x, keeping y constant dx, plus partial f by partial y, keeping x constant, multiplied by dy. And so this kind of has a similar form to this, really, doesn't it? It has, it has variable times change in variable plus variable times change in variable. So I can now kind of say that T is the partial derivative of enthalpy with respect to entropy, keeping pressure constant. If I just simply identify this T term as the partial derivative of entropy keeping pressure constant, using this form right here. So all I've done is I've compared this equation with this equation and therefore concluded that T must be the partial differential of enthalpy with respect to entropy keeping pressure constant. And I can also do a similar thing with volume. I can simply take the partial differential of enthalpy with respect to pressure, this time keeping the temperature constant. So volume is the partial differential of, keeping the entropy constant, not the temperature. So V is the partial differential of H with respect to P, keeping the entropy constant. Now what am I going to do? I'm going to differentiate these terms again. So what is the derivative of T with respect to P, keeping entropy constant? I want to do this cross derivative thing. I'm going to differentiate T with respect to pressure. So T dP dt by dP is therefore equal to d2h by ds dP. That is dt by dP. But what about this volume? What if I differentiate the volume with respect to entropy? Well, let's just use this hand side first. d2h by dP ds is equal to dV by ds at constant pressure. This should be at constant entropy, that should be at constant pressure. And so, what have we got here? Well, these two terms must be the same because of the fact that they're exact differentials. And so we've now derived that dt by dP at constant entropy is equal to dV by ds at constant pressure. And this is one of the Maxwell relations that I mentioned earlier. there are in fact 4 different Maxwell relations, and so therefore I'm not going to go through them all because there's quite a few. But as you can see, this is kind of useful for when you want to convert between different types of variables for different reasons. So it's the fact that enthalpy is an exact differential was the reason why this can work, and you can use this relation many times. So what are these other thermodynamic potentials? It's probably about time I introduced them. Well, let's just list them all out. So we've got the internal energy, which is U, and we've got the enthalpy, which is H, which we know about. But there's another, so the first new one is called the Helmholtz free energy, which is either A or F, depending on what you look at. But I'm going to use F, because that's the one that my uni used. And this is the Helmholtz free energy. There is another one called the Gibbs free energy, G. And there's another one called the grand potential, which is given the symbol phi. Now, the grand potential is kind of the odd one out of these 4 right here. These 4 right here are quite well linked, but the grand potential is slightly different. The grand potential more applies when n changes, so it more applies for open systems. So I won't be talking about the grand potential very much at all. Probably not until quite a bit later on in the series. It will return, but it won't come for quite a while. So how am I going to define these two right here, these two free energies? Well, the Helmholtz free energy is defined as F equals U, the internal energy, but I'm going to now subtract the product of its temperature and entropy. Now, there's quite a good physical reason for doing this, because if you subtract Ts, then you actually end up with what's called the free energy. And the free energy is basically the amount of energy that's available to do work, which has quite an important physical significance. And so that is what the Helmholtz free energy is. And the Gibbs free energy, well, the Gibbs free energy is actually kind of like a combination of both the enthalpy and the internal energy. So let's just write out what the enthalpy is again. So the enthalpy is U plus PV. And so the Gibbs free energy is U plus PV minus TS. So it's actually a combination of these two right here, the enthalpy and the Helmholtz free energy. And the grand potential phi is U minus TS. We're going to ignore it. It's not got anything to do with PV, and we're going to subtract mu n. But of course, this doesn't really matter quite yet. We're not going to be talking about the grand potential very much. But it's just there, just so you know what it is, I suppose. So in this column here, I'm going to write out what are the differentials. So what is it for you? Well, for you, it was the fundamental relation of thermodynamics. So it's T ds minus P dV. That was it for you. With the enthalpy, that we found that dH was equal to TdS yet again, but rather than minus PdV, it was plus VdP. And so we found that entropy and pressure were the natural variables of H. So let's do this for the other two. I'm not going to do the grand potential. So what are we going to get when we take the differential of the Helmholtz free energy? Well, F equals U minus Ts. So let's do exactly what we did before. dF equals du minus, so we're going to take the full differential of Ts, so we use the product rule again. So we're going to get T ds plus S dt. But what's du got in it? Well, du has a TdS already in it. So TdS minus PdV minus TdS plus minus S dt. Well, these two TdS terms are now going to cancel. And so now we get that dF is equal to minus PdV minus S dt. So we've now got that for the Helmholtz free energy, the natural variables are now volume and temperature. Those are the natural variables of the Helmholtz free energy. And lastly, for completeness, let's do the Gibbs free energy. So G equals U plus PV minus TS. So let's take the differential. dG equals du plus product rule part 1, P dV plus V dP minus the next product rule, T ds plus S dt. And so what we're now going to do exactly what we did, substitute in what du is, which is T ds plus minus P dV. And we're just going to add all these other terms, which I'm going to copy and paste because I'm very lazy. So there we go. And as you can see, we're going to get a lot of cancellations happening. So we can wipe off these two TDSs and we can wipe off these two PdVs. And so we get that the change in the Gibbs free energy is equal to V dP minus S dt. V dP minus S dt. And so we now got the natural variables of the Gibbs free energy are the pressure and the temperature, which is why the Gibbs free energy is used in chemistry a lot, because the temperature and the pressure are the easiest things to keep constant. And so the Gibbs free energy is actually used a lot in whether a reaction is energetically favorable. We use the Gibbs free energy. If the reaction is energetically favorable, dG is negative, and dG would be positive if the reaction is non-energetically favorable. And this is so that's why it's used a little bit in chemistry. So those are the differentials for the Helmholtz free energy and the Gibbs free energy. The Helmholtz free energy is minus PdV minus SdT, and the Gibbs free energy is VdP minus SdT. And so there we go. So we can now identify what the natural variables are of all of these thermodynamic potentials. So we know that for the internal energy, the two natural variables are entropy and volume. For the enthalpy, they were entropy and pressure. For the Helmholtz free energy, they were volume and temperature. And for the Gibbs free energy, they were pressure and temperature. And so there we have it. These are our four thermodynamic potentials. It's quite a nice little mathematical formulation. And so there we are. And of course, you can use each one of these, just like we did with the enthalpy, to derive the Maxwell relations. So you're going to get lots and lots of different Maxwell relations. Actually, I say lots, there are only 4. And they're all great for when you want to convert between different variables. And so there we go. I'll see you guys in the next video.